Hello everyone, and welcome to another part of the Galaga SDL tutorial videos. And in this video we're going to finally finish our collision detection system. So we will be implementing our BoxBox collision detection, and we will also be fixing a few problems with the box circle collision, and there is a problem with the position of an entity in the framework that we need to fix. So let's start first with our box circle collision detection. In the last video, we were checking if the circle lies on one of the edges of the box or if the circle is inside the box. But the thing that we didn't check for is if the box was inside the circle instead. And this is a relatively easy thing to check for. So what we're going to do is take our array that we created and put it here at the top. And then we will create two new variables. The first one will be float radius, which will be the radius of our circle. So the radius is going to be equal to circle get radius. And we will also have a vector 2. And that will be our circle position. So circle pos, which is going to be equal to circle position. And these are the two variables that we need right now. Next, what we're going to do is say for int I equals 0, I is less than 4, I plus plus. And as you might have guessed, we are looping through to check every index of this array. And we'll say that if our quad at I minus the circle's position dot magnitude is less than the radius of the circle, then return true. So basically what we're saying here is that if we have a box and we have a circle, well, that's not really a circle, but there we go. So if any of the verts of the box, the distance from that vertex to the center of the circle, if it's less than the radius of the circle, that we know that this vertex is inside the circle and there is a collision. That's basically it. And the reason why we put it here at the top is because it's much less processor intensive than these things. So if we can check for this first and just return true right away, that's much better for us. And we might as well use the position variable for other things as well. So for example, these ones here. So we'll just use circle position here. Since we have a radius, let's just use it here as well. So we're just replacing these with circle position and radius. And we also have it being used here. So we will just replace this one with circle position. And that's pretty much it for the fix to the box circle collision. And that will be it for that. Now let's move on to our BoxBox collision detection. Over here, we will create our inline boolean function, which we will call BoxBox collision. So just like what we did before, we will have a box collider pointer called B1, a box collider pointer called B2, and that will be it for our function. Now, next up, we are going to declare a few variables that we need for the separating axis theorem. And now I want to take a moment to actually explain what this theorem says and how it works. So the idea is, let's delete these. If we have a box, and let's say this is one of our boxes, and let's make another box that's actually rotated. So this is our second box. What the theorem is saying is that if we project along the normal of each side of that box, and that works for all polygons, but they have to be convex. They can't be concave polygons. So, and a box is a convex polygon, so we can use it for that. If we project along every normal of each side, so a normal of the side is a perpendicular line pointing away from the center of the object. If we project along every one of these normals, and if there is overlap, so the first square, of course, has 4 normals, one for each side, and the second square has 4 as well, 1 for each side. And if we project along every one of these normals, so let's say we're projecting along this one here, this one would be coming down here, 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 and there. and this one will be here, 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 and here. And if we go get the minimum point and the maximum point, and we have a minimum point and a maximum point for this one as well, if there is any overlap between these two lines on all axes that we project on, that means there is a collision. If there is no overlap on a single axis, that means that there is no collision. And this is what we're going to be implementing. But you'll notice that this normal over here and this over there are pretty much negatives of each other. And this one are negatives of each other. So all we need is to project on one of them, not both. So what we can do is to only project on this, and it will be as if we projected on these as well. And that is just an optimization that we can do so that we don't have to check 4, but we can check just 2 instead. And the same thing for this square over here. We can just check this and ignore these 2. And that's what we're going to be doing. So the first thing that we're going to do is do a vector 2 projection axis, so proj axes, which is going to be 4. And the reason why they're 4 is because we have 1, 2, 3, 4. 2 axes for each box. Next up, we are going to create the normals for these boxes. So projection axis at 0 is going to be equal to B1 get vertex position at 0 minus B1 get vertex position at 1. And of course, since these are normals, we need to get them normalized. So dot normalized. And for the second one, we are going to be pretty much copying and pasting this, but this one is going to be at 1. And this one is going to be get vertex position at 0, and this one is going to be get vertex position at 2. Now, you might be wondering why we're going along the side of the box. And the idea here is that if we are going along the side of this box, it's exactly as if we're getting the normal of the side that's perpendicular to it. And that's pretty much what we're doing. And you'll remember that if we get this normal or this normal, it doesn't matter. We just need to project along one of these. And that's what we're doing. We're going, this is our 0, this is our 1, and this is our 2. So we're going from 0 and 1. So we're subtracting from here. So we're going over here, right? So this one is pointing this way, and this one is pointing that way. So we're getting this one and this one right here. And this is getting very messy, but there we go. So we're getting this one and this one right here. And then we'll do the same thing for the next box. So we'll say that our projection axes, so we can just copy and paste these, but change these to 2 and 3. And of course, this one will be box 2, box 2, box 2, and box 2. Now we have all our side normals that we need. Next up, we need a few variables. So I mentioned before we need the minimum and the maximum projection for each box. And these are the variables we're going to be creating next. We're going to have B1 minimum. It's going to start off being 0. And this, of course, is a float. And then we're going to have B1 max. It's going to start off as being 0 as well. Now we're going to have B2 min, same idea, 0, and B2 max, which is going to start off at 0 as well. And finally, we're going to get a float projection 1, which is starting off at 0, and projection 2, which is going to start off at 0. And projection 1 and 2 is just going to be our point of projection as we go through each vertex. That's what we're going to be using these two variables for. Now, let's start by looping through all our projection axes. So since our projection axes are 4, so we'll do 4 into I equals 0, I is less than 4, I plus plus, and then 4 in j equals 0, j is less than 4, and then j plus plus. Now, the main reason why j is 4 is because our boxes have 4 verts. So we're going through 1, 2, 3, 4 projection axes, and for each axis we're doing 1, 2, 3, 4 verts. And since both boxes have 4 verts, we can do 1, 1, 2, 2, 3, 3, and 4, 4. We can do both boxes at the same time, and that's why we're looping 4 times. Okay, so now we'll say our projection 1 is going to be equal to the dot product of B1 get vertex position at J and projection axis at I, and then our projection 2 is going to be equal to the dot product of B2 get vertex position at J and projection axis at I. And as I said before, we're doing both boxes at the same time. So we're getting the J's vertex of B1 and B2 and projecting it onto the same axis inside this loop. Okay. Now that we have our projected point, we can say that if J is equal to 0, we're going to say that our B1 min is going to be equal to our B1 max, which is going to be equal to the first projection. And B2 min is going to be equal to our B2 max, which is going to be equal to our second projection. So if this is the first point that we're projecting down, our minimum and maximum is going to be the same point. And that's what we're basically saying here. Now, what if J is not equal to 0? Now, else, we're going to say that if the projection at 1 is less than B1 minimum, then our B1 minimum is going to be equal to our projection at 1. And if the projection at 1 is more than B1 max, our B1 max is going to be equal to our projection at 1. So what we're saying here is we have our projection. If our projection is less than our minimum, so let's say we started with this one, which is 0. We started with this one here, and we projected both our points, and our min and max are right here. Now we projected point at 1. Our minimum is the same, so we're not going to change it, but our maximum now needs to change. So now this is going to be our new B1 max. And that's pretty much what we're doing. And we need to repeat the same thing for the second box. Oh, by mistake here, I wrote box 2 max. So this one is box 1 max. We're only dealing with box 1 right now. And then we can just copy and paste this, and then change all the 1s to 2s. So if projection 2 is less than the B2 minimum, we need to set the B2 minimum to be projection 2. And projection 2 is more than B2 maximum, we need to set our B2 maximum to be at projection 2. And that will be it for these two if statements. Now, next up is to check if there is overlap or not, because remember, if we don't have an overlap on one of the axes, then there is no collision. So if there is no overlap when we do the projection of all 4 points down on that one axis, if there is no overlap, we can just stop the collision detection right there. So we're doing this right after we finish projecting all 4 points, so outside the inner for loop. We'll say that float midpoint 1 is going to be equal to B1 minimum. Oh, first we need to find the distance, half the distance from the minimum and maximum. So float half dist 1 is going to be equal to B1 maximum minus B1 minimum, and that will be times 0.5f. So 0.5f. So we're getting the distance, half the distance between min and maximum. So we want this distance right here. So we're taking the maximum, subtracting it from the minimum, multiplying it by half to give us this distance right here. And then our midpoint will be our B1 minimum plus half the distance 1. Same thing for the second box. So that will be half dist 2 is going to be equal to B2 maximum minus B2 minimum. And then our midpoint 2 is going to be equal to B2 minimum plus half distance 2. And that will be it for the 4 variables that we need. And now we can find the overlap. And we'll do this basically just like a circle collision, because now we have a midpoint, we have half the distance, which is like a radius, and we'll say that if the distance from half of one, or the midpoint of one and the midpoint of the other one, if the distance between these two is less than the two halves added up, that means that there is a collision. So we can say if midpoint 1 minus midpoint 2, of course we'll put these between brackets. So if the distance from midpoint 1 and midpoint 2 dot magnitude, well, why was I thinking that this is a vector? If the absolute distance from midpoint 1 minus midpoint 2, which is basically like getting the magnitude, what we're going to do is to say if that absolute value is less than, or more than actually, if it's more than midpoint or half distance 1 plus half distance 2, return false. Okay, so if the absolute distance from midpoint 1 and to midpoint 2 is more than half the distance 1 plus half the distance 2, we know that there is no collision, and if there is no collision on one axis, there is no collision at all. And this is, so we're just returning false. And then all the way here at the bottom, we're going to return true. And that's it. That's pretty much it for separating axis theorem. Now, we can test it, but when I was testing this out before, I found that there was an error in the framework, which was the position of our game entities. So if we open up our GameEntity.cpp and go down to our position, what is happening right now is that it's only taking into account the rotation and the position of the parent, the first parent, and it's ignoring the parents after that. And since we have in our colliders, so if we go to our box collider.cpp, we have the box collider as a child of our enemies, and the points inside the box collider, which are the verts, are children of the box. Since our position is not taking into account the second parent, we were getting wrong values. So let's fix that. So we'll open up our GameEntity.cpp, and in our position, what we're going to do is to actually loop through it with a do-while loop. So we first need two variables. So the first one will be GameEntityPointer. We'll call this one parent, which is going to start off being mParent. And a vector2 final position, which is going to start off as mPosition. Actually, we also need parent scale, and our parent scale is going to be equal to a vector2 underscore 0. Now, parent scale we're using here, so we're going to just replace this with that. So we need our do-while loop, so we'll do do-while parent. So as long as the parent is still valid, because we're going to be switching parents. And then in here, we'll say that we'll take the same thing that we're doing here. So our parent scale is going to be equal to our parent scale instead of world, we'll do locally. Since now we're looping through all the parents, we don't need to do anything in world position or world scale. We can just do it exactly like we are doing matrix multiplication, and I'll explain that in a second. So we have our parent scale, which is our parent scale locally, and then we'll say that our final position is going to be equal to the rotation rotate vector of vector2 final position dot x multiplied by our parent scale dot x and final position dot y multiplied by our parent scale dot y. Now, we are rotating this vector by our parent rotation local. Okay, so we're taking our parents, the final position, our final position right now, and multiplying it by the parent scale, just like what we were doing before, but now we are rotating by the parent's local rotation, and that's it. And then next, we're doing final position plus equals the parent's position locally. And then after that, we'll say parent equals mparent, or parent parent. So not mparent, just the parent is going to be equal parent parent, which is we're getting the parent of the parent, and so on. We're looping through until we run out of parents, and then we exit the loop. Now we don't need this anymore, so all we need is to just say return final position. And that will be the fix that we need. And I'll take a moment now to explain what we're doing here. So the idea here is that, let me erase this for a second. And when we have in linear algebra, when we're multiplying, when we're trying to scale, rotate, and translate, what we're doing is we're taking our point. So that's going to be P. We're applying our scale, rotation, and our translation, right? So what we want to do is to first, so let's say we have our scale. So we want to multiply our point by our scale, and then take this matrix and then multiply this matrix by our rotation, and then finally take this matrix and multiply it by our translation. And this way our translation doesn't affect our rotation doesn't affect the scale, and so on. So what we're doing is we're taking, and keep in mind all this is local, so our translation, rotation, and scale matrix multiplied by our point, these are all local. So for each object, these are done locally. And what we're doing here is taking our parent's local scale, we're taking the scale, multiplying it by our final position, which is our point, and then we are rotating our point, which is doing this one right here, and then finally we are translating, which is what we're doing right here. So we're kind of mimicking matrix multiplication to get our scale, rotation, and translation, but in a while loop instead, since we don't have a matrix multiplication library yet. And that's pretty much it. The problem before is that it wasn't actually taking into account the local space of each object separately. It was trying to just add the world position of the parent and taking the total rotation of the parent, and that was not correct. And that's it. So let's try to run our game and see how it goes. Okay, so it looks like there is an issue with our BoxBox collision, and that's most likely because we're not even taking it into account yet. So let's go back to our physics helper, and over here we're not saying check our BoxBox collision, so we'll say else if, of course this is inside our collider check, C1 get type is equal to collider type box, and C2 get type is equal to collider box, and then we can return BoxBox collision, and we're going to do a static cast into a box collider pointer of our C1, and the static cast of a box collider pointer of our C2. And we need a bracket here, and that will be it. Okay, let's give this a try. Also, what we can do is say else, return false, just so that if none of these apply, just return false. Okay, and let's see how this goes. There we go. So as you can see, our collision detection is now working for 2 boxes. We also need to reactivate the collision detection for the butterflies. So let's go to our butterfly.cpp and let's go down here and let's re-add the box collider, and we can erase the circle collider that we had before and then rerun this. I will probably be going to the framework videos and fixing this problem because this is a big issue, the position problem that we fixed. But that will probably be after I finish this game. Okay, so now the butterflies have it too, and there we go. Now our box collision detection is working, and that will be it for our collision detection for this game. And this will be it for this video. I really hope that this video helped. If you have any questions, suggestions, or feedback, please leave them below. Otherwise, thank you very much for watching, and I will see you in the next video.